Hello, today we're looking at topic 3.12, equivalent representations of trig functions, day 2. Last time we focused on all our new identities and how to simplify with the identities, how to derive the identities, and we learned how to work with them in general. Today we're going to use those same identities and we're going to remember our solving techniques. So this is a quick checklist. I will load the color-coded one into Canvas. So if you pull this document up tomorrow, you'll have a color-coded page here that kind of bullet points are one color, what's underneath it is a different color. It just makes it a little easier to find things. So I went ahead and highlighted the bullets here. So as we're talking on the video, we can address them. So in what we're doing today, we're going to use standard algebra techniques. That means we're going to do things like collecting like terms and factoring. When you have one trig equation, you're going to move that to one side of the equation. So you're going to isolate the trig function. If you have two trig functions in the equation, then you're going to move them to the same side and then figure out how to separate them. So it's okay to have more than one type of trig function as long as when you separate them, they're in their own factor. So tools that you could use here would be like factoring or maybe using a trig identity. This could produce an answer that does not, or an equation or something that doesn't yield a solution. So keep that in mind. We're going to represent all possible solutions as an equation. And yes, it could be in all four quadrants, but that doesn't mean we're going to write an equation for all four quadrants. So we're going to use our general form. We're going to use our K, and we're going to remember that K is in the set of integers. So that's one way. If it gives you a restriction, then we'll have a list of answers just like we have solved previously. Answers are going to be exact, no decimals. One thing to remember when trig functions happen, if you square both sides, then you can produce extraneous solutions and you'll need to check for those. Never divide both sides of an equation by a trig function because that will cause you to lose solutions because you're going to divide out trig pieces, which could possibly produce solutions. Then we're going to solve the equation. Some of them might be multiple angles or have horizontal dilations. And so that's going to work very similarly to when we did vertical asymptotes. So we'll follow that same kind of procedure, except we might have some lists to adjust instead of just an equation. When we are doing our equations with no restrictions, remember we need to see our Kes and the double bar Z, remember that's just a symbol for integers. And so solutions within the restriction will be listed out and paying attention to what that restriction is. So maybe it's 0 to 2 pi, maybe it's 0 to pi, maybe it's pi over 2 to 3 pi over 2. So always pay attention there. And then right now we're going to work through these three examples so you have something to look at and refer back to in your notes. So notice the first one says all possible solutions. So this one is going to be equation answers. These two both have restrictions, so we'll have a list, but notice that there is a horizontal dilation on question 3. So we're going to have to make that adjustment of our list just kind of like we did vertical asymptotes. Once you finish these 3 questions, then you are going to work out these 4 questions in class and practice with the identities some more at your table groups. And then you have the backside of last period's daily practice to work and make sure you're ready for our progress check on topic 3.12. So we did our first read a moment ago. So our second read is we're solving, so the unknown in here is x, so that's going to be in the form of an x equals, and I will need to set it equal to 0 to solve. So here's what I'm trying to solve, and it says for all possible solutions without any restrictions, so that means my answer is going to be in the form of an equation. Okay, so that's our second read. So now we're going to jump into the problem. So in order to solve this, I'm going to write it down once. Cotan x cosine squared x equals 2 cotan x. And in order to solve it, remember I need to be equal to 0. So I'm moving all the trig functions to one side of the equation and setting it equal to 0. So once I move the 2 cotan over, now I'm looking at this side of the function and I'm thinking of it kind of like a binomial. So we have this piece and this piece. So what do they have in common? They have a cotangent in common. So I'm going to take out that common factor of cotan x, which is going to leave me with cosine squared x minus 2 equals 0. So now I have two factors, one here and one here. So just like we have in all our previous equations, we're going to set cotan x equal to 0. So remember, cotan is cosine over sine. So that means in order for this to be 0, I'm looking for places on my unit circle where cosine is 0. And that's going to happen right here at pi over 2 and at 3 pi over 2. Okay, so that, remember, I'm looking for cosine of x equal to 0. That's how I use that reciprocal piece there, or in that case, I use the quotient identity. Then we're going to take this piece and we're going to say cosine squared x minus 2 equals 0, cosine squared x equals 2, and cosine x equals plus or minus square root of 2. So again, just solving. What I should recognize here is that the square root of 2 is a little bit bigger than 1, and we know that the maximum value of cosine is 1, the minimum value of cosine is negative 1. So this is a little bit bigger than 1 and a little bit less than negative 1. So I am not going to have any solutions that are produced from here. So I'm going to use my empty set, and then I'm going to say that this is outside the range of cosine of x. So then when I get to the point of actually listing what my solutions are, remember I listed that my solutions should look like an equation. So I'm going to look at what I'm solving for, which is x. So I'm going to say x equals, I'm going to use my smallest angle, which is going to be pi over 2. I'm going to add pi to get from here to here. And I need to make sure that when I'm adding that pi, I'm keeping it in whole pi rotation. So 1 pi, 2 pi, 3 pi, 4 pi, so on and so forth. So I need to qualify this and say that k is going to belong into the set of integers. And you can use the symbols or you can write that out in words. And that's our first equation. Okay, so we already did our first read when we looked at the document a moment ago. So second read, marking it up, solve means I'm going to go x equals, because my unknown in the problem is x. Here is my equation, in which I should notice right off the bat, I see two different types of equations, but I also see that we have a power of 2, a power of 1, and some numbers. So that's going to be a factorable form. And here it still says for all solutions, but notice it gives us a restriction right here. So if it has a restriction right here, then my answers in the end, my solution is going to be a list. All right. So first off, we want to move everything to the same side, and we want this set equal to 0. Once we have this set equal to 0, we should be noticing that we have two different trig functions, so I can't factor or do anything with that. So since there's nothing else, no GCF to take out that's going to separate them, I'm going to use an identity. So if you notice, we have a power of 2, then a power of 1. I don't have an identity that's going to change the power of 1 to a power of 2, but I do have a Pythagorean identity right here that I can use, and I can rewrite sine squared x as 1 minus cosine squared x. So remember, the identity is sine squared x plus cosine squared x equals 1. So if I want to move the cosine to the other side, then I can just subtract that. So I'm going to replace this with my Pythagorean identity. So I have two parentheses, and then I'm going to have 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. And so what I did here, now by using this, I can distribute my 2 through, and I can actually have and rewrite this so that it is some sort of trinomial type form equal to 0. So when I distribute through, I'm going to have 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. So I'm going to pull my power of 2 term first. And then I have a positive 2 and a negative 3, so that's going to be negative 1. But I still don't want to factor when my a value is negative. So I'm going to divide a negative 1 out of everything, which is simply going to flip all these expressions, and then I can divide both sides by negative 1 to get rid of the negative 1. So what I mean by that is I'm going to pull out the negative 1, 2 cosine squared x, which is going to change this sign, which is going to change this sign, equals 0. Now, I don't have to keep that negative 1 there because if I divide both sides by negative 1, 0 divided by negative 1 is 0. Negative 1 divided by negative 1 is positive 1. So I'm left with the trinomial equal to 0. Now, I don't really expect to see that in your work, but sometimes that confuses people why we can divide through. So I always, at least once, like to remind you from Algebra 2 why that works. Okay, so now we're going to factor. So we know it's going to factor to two binomial forms. The factors of 2 are 2 and 1. The factors of cosine squared are cosine x and cosine x. And then the factors of 1 back here are 1 and 1. And I need them to add up to be a -3. So they're both going to be negative. Various ways to factor, but that's basically the gist of getting to this point. All right, so now we're going to set each factor equal to 0. We're going to set each factor equal to 0. So I'm going to get cosine x. I'm going to move the 1 over, divide by 2. So this is 1/2. Then I'm going to set up my angles. So cosine is positive in the first quadrant and the fourth quadrant. And in the first quadrant, cosine of x is 1/2 at the angle pi over 3. So the multiple of 3 angle in the fourth quadrant is 5 pi over 3. So then we do the other factor. So cosine of x minus 1 equals 0. So cosine of x equals 1. And the only place cosine of x equals 1 is at 0. So if you remember from the beginning, we said on this problem that this was going to be a list. So my solution is going to be the unknown of x that I'm solving for, equals, and I'm going to have a 0, I'm going to have a pi over 3, and a 5 pi over 3. And so those are going to be my solutions for this problem. When we're doing this kind of problem, I don't personally care the order. It is a little easier for me if you just keep whatever solutions you get from this factor together and whatever solutions you keep this factor together. If it were on Canvas, you might be asked to type in a certain order or something like that. But an open-ended question or FRQ type style question, I am fine as long as I get all of my solutions here and you don't forget something from one factor or the other. All right, so that was, first one was an example of answers that look like an equation. The second was an example of answers that are going to look like a list. And so let's move on to our final practice on number 3, and then I will turn you loose with your table groups or your groups in class to work the 4 problems for the rest of the notes. Okay, so we already did our first read on problem 3. So let's look at what we have. So we're solving again. So we know that's going to be x equals. We have this function right here, which has had a horizontal dilation. And remember, that's looking at this part right inside here. We're doing for all solutions, and we're going to have a restricted area. So our final answer is going to be a list. So that's us marking up the problem. So let's talk about a few things here. This problem right here with this horizontal dilation can be the same thing as tan squared of 1/2 x minus 1 equals 0. So that's kind of how you can think of it. And when you're thinking of it in this particular form, then we're looking at the fact that this in here is a horizontal dilation by a factor of 2. So what that's going to do to this particular problem is it's going to actually adjust the restriction from where we're looking. Because think about this, if this is 1/2 dilation, then that means it's actually stretching it out to be twice as long as it once was. So our solutions are going to come from twice as long of an area. So for that adjusted domain, or the adjusted area where we're looking for our solutions, then originally that would be 0 less than or equal to x less than or equal to 2 pi. Remember, in our problem, however, it's 1/2 x in here, not just x, right? And then if it's 1/2 in here, that means it's dilating or it's stretching out by 2. So what we're going to do is adjust this, and I'm going to multiply everything here in my solution area by 2. So 0 less than or equal to 2x less than or equal to 4 pi. And so remember, we said twice as long. So if it originally was going to 2 pi, another rotation around the circle, so you're going around the circle twice, it's going to take us all the way out to 4 pi. So it's always a good idea to kind of get this adjustment jotted down before you start the problem. All right, so now we can begin. So we're going to follow the same procedures that we did with vertical asymptotes. So we're going to generate our list of angles based on if we were going to solve this as tangent squared of x minus 1 equals 0. So we're going to think about it in terms of just a plain old equation. And then, like we did our vertical asymptotes, then we will adjust at the end. All right, so if we're solving this, then we want to get down to my x. So I'm going to do tangent squared of x equals positive 1. And then to get tan squared down to tan x, I'm going to take the square root. It's become plus or minus 1. I started to write the square root of 1 there, guys. Sorry. 1. All right, so that's where we get to our point in our work. And so we know now, based on what we're doing right here, that positive and negative means that I'm looking for 4 angles. Tangent can be positive in 1 and 3 and negative in 2 and 4. So basically, I have a solution in all 4 quadrants. So that's going to be pi over 4 in the first quadrant, 3 pi over 4 in the second quadrant, 5 pi over 4 in the third quadrant, and 7 pi over 4 in the fourth quadrant. So we have 4 possibilities. But now we're going to go back to our equation. So that was like kind of the process that gets me to what I'm solving for. Okay? Now we're going to actually write our equations based on what we need to solve. We need to know what 1/2 x equals, not just what x equals. So I'm going to write my equations down here as 1/2 x equals, and then I'm going to list these angles out. Just like when we did the vertical asymptotes, we listed everything out first and then we adjusted. So I have, instead of an equation here like vertical asymptotes, I have a list of angles that I'm writing down, and then I'm going to adjust the whole list. All right, so that's step 1. We solve it as if it's x. We write down what we're actually solving for, which is this piece right here, the 1/2 x, and that's where I get this initial list. But this is not my answer. My answer is going to be the result of our adjustment. And so what I'm going to do is I'm going to take this 1/2, I'm going to write it again so we don't lose track of this. All right, and so now we're going to make the adjustment. So I don't want to solve for 1/2 x, I want to solve for x. So what should I multiply 1/2 by to turn it into a 1 so that I can have my answers of x equals? I'm going to multiply this whole statement by 2. Okay, so as I multiply 2 times 1/2 x, then I'm going to get x. Oops. You know what? I'm going to write down that this is my solution like I did on the other ones. Solution. All right, so I'm going to do 2 times 1/2 x, which is going to give me x. And then I'm going to do 2 times pi over 4. So that's 2 pi over 4, which is going to simplify to pi over 2. Then I'm going to do 2 times 3 pi over 4, which is going to simplify to 3 pi over 2. Then I'm going to do 5 pi over 4, which is going to simplify to 5 pi over 2. And then I'm going to multiply 2 by 7 pi over 4, which is going to simplify to 7 pi over 2. And it simplifies, remember, because as we're doing this distributing here, so you're doing 2 over 1 times pi over 4. So that's going to simplify to 2, which leaves me with pi over 2. So if you weren't understanding why it simplified, you do this for each distribution of that 2. So now I have my solution list. All right, so now in class, whether you're in your table groups, board groups, however your teacher is working on that, you are going to be looking now, you have some practice and some examples to look at. You're going to work through these 4 questions with your group, and then you'll go over those answer solutions with your teacher. All right, so make sure once you do your 4 problems in class, then you immediately go and do the back side of your daily practice so you have lots of practice on solving these equations so you will do really well on your AOL. Remember, we'll have a progress check coming up so that you can get some feedback and know where you need to zero in and brush up and strengthen before you have an AOL for the class. All right, guys, thank you. See you next time.